In this video, going to explain how to do proof by contradiction. So proof by contradiction is a method to make your proofs probably much quicker. Sometimes it's not easy to prove something is true. It's much easier to prove that it's not true, get stuck, and then hence prove that it's true. So it's a technique you learn after a couple of practices, or actually after seeing a couple of examples. A famous proof by contradiction is to show that the square root of 2 is an irrational number, so you can practice with that, but in this video I'm going to explain the square root of 3 is an irrational number. So it's much easier to assume, so we're going to let square root of 3 be a rational number, so we're going to make it equal to p over q. But to ensure that it's a rational number, we need to make sure that p and q are integers, but also p and q have no common factors. So the trick with proof by contradiction, just like direct proofs, is to manipulate with algebra and then get stuck at some point. So the best thing to do right now is to square both sides, so you end up with 3 equals to p squared over q squared. And then let's say you cross multiply, so I end up with 3q squared equals to p squared. Now I'm going to explain something that might not seem intuitive, but it's a fact that you could use from now on. So in this statement, I could say that 3 divides p squared, which therefore implies that 3 divides p. So how is this true? Is you could say that if you have 3q squared equals to p squared, so p squared is just p times p. If I divide both sides by 3, this will simplify to q squared, which is an integer being squared. And any integer being squared will always give you another integer. So this is an integer, which means that 3 has to divide p squared. So this statement is true. Now if 3 divides p squared, so it has to cancel out with 3 has to exist as a factor of p here, or obviously p there as well, which means 3 divides p. You might say, well, maybe there was a number here that I multiplied with another factor here and it gave me a 3. Well, we know the 3 is a prime number, so there's no way. I mean, we could say 1 times 3, but if 3 exists as a factor here, then 3 exists as a factor here. So you'll soon think, well, that doesn't work with 3. Well, that's the point. We have to get to a contradiction with 3. It would work with other composite numbers. So 3 divides p squared, so 3 divides p, which means that p can now be written as something like 3k, where k is an integer. Because we said 3 divides p. So now I have two ways of writing p squared. I could either say it's 3k squared, or it's 3q squared, and the q squared comes from here. So just rewriting this would give us 9k squared equals to 3q squared. Dividing both sides by 3, I'm going to get 3k squared equals to q squared. And the same assumption can hold here. So if 3 divides q squared, then 3 divides q. Which means that q and p have a common factor of 3, and that is our contradiction, and this is the symbol for contradiction. You don't have to use it. This is more university level symbols and not school level. So you can just write contradiction. Therefore, square root of 3 is an irrational number. Because we've assumed that q and p have no common factors. Again, as I mentioned, because if they did, they're going to be integers and it's going to simplify out. So then we can no longer, would still be a rational number, but then it doesn't make sense. We want to prove that it's irrational, so we have to prove that it's rational, try and prove that it's rational, get stuck, and therefore it's irrational. So this is where the contradiction came in mind, and everything was correct algebraically. Even this statement is correct algebraically. The only assumption we've made is the beginning, which means our beginning is incorrect, and therefore square root of 3 is an irrational number. So doing something similar for this, we have n squared plus 2 not equals to 4k, and if I want to prove it, it's going to be a bit hard. So let me prove the opposite. So I'm going to say, let this happen, and hopefully by algebraic manipulation I'm going to get stuck at some point. So let's divide by 4 first. So I'm going to get n squared over 4 plus 1 over 2. And I can rewrite this to get n over 2 squared plus 1 over 2 equals to k. Again, notice how n divides by 2, and I should be getting an integer. So this implies that, because my assumption here is that n squared plus 2 equals to 4k, so everything is nicely an integer. And so if I'm dividing by 4, I should still get an integer. So all of this should simplify to an integer, which means n over 2, my integer answered squared, should give me an integer plus a half, and so on. So it's all about knowing your integers. So this just implies that n is divisible by 2. And so n could be written as 2k, where k, sorry, not k, k is being used, is 2m, where m is an integer. So I can rewrite my n over 2, and I could rewrite it as 2m over 2 squared plus a half k equals to k. This will simplify to an m squared plus a half equals to k. Hopefully you've spotted the contradiction by now. Moving things around, I'm gonna I'm gonna have m squared minus k equals to a half. And this is my contradiction, because you can't have integer addition or subtraction resulting in a rational number. Now we could get a negative, that's fine, but we can't get a or a non-integer is more accurate, because a non-integer number. Okay, so therefore n squared plus 2 is not equal to 4k. So this is where our contradiction comes in. So there's no way you'd have an integer squared minus another integer that would give you a non-integer number, keeping that in mind. The last type of contradiction is actually a counterexample, so that falls under the contradiction. So this question is actually, I didn't write the full question down, but it's proof by counterexample these statements. So they've given us a statement, 2 to the power of n minus 1 is a prime number for all n belonging to the natural numbers. And I want to give a counterexample to the statement to make it false. And sometimes they'll tell you to give a counterexample rather than you assuming that you have to give one. So it's hard to do a proof by contradiction or a direct proof, because you want to directly show that it is or is not a prime number, and we have no algebraic way of defining prime numbers, so it's really hard to do it, and the best way is to just show by an example. Now, there are many prime numbers that exist using this method, which is why this assumption might seem true, but not all prime numbers are defined as such. If they were, then this is the perfect algebraic way to define a prime number. So testing out numbers, we can't do 0 because not everywhere they don't use 0 as a natural number. In every publications of math, so we won't assume that it is here. The simplest one is to substitute n equals to 1. Any substitution that would be a counterexample is okay. So if I substitute it in here, I'm going to get a1, which is not a prime number. If you want to go further, just with trial and error, you'll notice that 2 to the power 4 minus 1 is 60 minus 1, which is 15, which is not a prime number. And that's it. You've shown it by a counterexample. So that's the idea of it. And usually it's going to show whether you should use a counterexample or a proof by contradiction.